Today we will discuss about some of the end semester questions and try to review the answers of these questions. So, the first questions that we will like to address are some short answer type questions. So, let us go through the first question. We need to answer these questions in brief. First question is for flow through a porous medium. For flow through a porous medium, the distributed resistance to flow is expressed by the source term So, this is a source term for the x direction momentum equation which represents a resistance against flow through a porous medium. Here C is a positive constant and u is the velocity component in the x direction. The question is, write the best linearization of the source term by giving the expressions for SC and SP. That means you want to express S is equal to SC plus SP UP. So, you have to find out what is SC and what is SP. So, let us quickly see how to do that. Of course, it is quite straightforward, but we have to consider, because mod u is there, we have to consider two different possibilities. One is u greater than 0, another is u less than 0. So, if you have u greater than 0, then S is equal to minus C u square, because mod u is minus u, mod u is u, so it becomes minus C into u into u. Now, for source term linearization, what we can do, we can find out a tangent to the SU curve that linearizes the source term. So, S minus S star is equal to ds du at the point star into u minus u star. This is the formula that we are going to use. So, at star point C is equal to C u star C u square is C u star square, and remember that C is given greater than 0. It is given in the problem that C is a positive constant. Now, S minus S star is S plus C u star square. So, what is ds du is equal to minus 2 C u. So, minus 2 C u star into u minus u star. So, S plus C u star square is equal to plus 2 C u star square minus 2 C u star u. So, S is equal to C u star square minus C minus 2 C u star u. So, you can see that you can write is that SC plus SPU. So, then what is SP? SP is equal to minus 2 CU star. By the basic, one of the basic rules, you must have SP equal to what? You must have SP as negative. So, you can see here that we have assumed u as greater than 0. So, u star is also greater than 0 and C is greater than 0. So, minus 2 C u star is less than 0. So, that will work fine. So, this is the linearization for u greater than 0. For u less than 0, you will have ds. So, for u less than 0, you have S is equal to C u square, because mod u is minus u for u less than 0. So, ds du is equal to 2 Cu. So, from the equation S minus S star equal to ds du star into u minus u star, you have S minus C u star square is equal to 2 C u star into u minus u star. So, S minus C u star square is equal to minus 2 C u star square plus 2c u star u. So, S is equal to minus c u star square plus 2c u star u. So, if you write this as again Sc plus Sp5 Spup, then this is what is SCC. It does not matter whether Sc is negative or positive. So, the sign criticality is there with Sp. So, this is Sp, and because u is less than 0, u star is less than 0, c is greater than 0. So, Sp is less than 0. So, that means this source term linearization is also fine. So, for both u greater than 0 and u less than 0 you can get expressions. You can combine these two expressions of course by expressing the entire thing in terms of mod of u again, but we just do not go into that details for this review. Now next question. Next question is, consider the following quadratic form. We will express a quadratic form. What is the quadratic form? The quadratic form is fx equal to half x transpose Ax minus b transpose x plus c, where A is a square symmetric matrix, x and b are vectors and c is a scalar. If x tilde be the solution of the system Ax equal to b, if x tilde be the solution of the system Ax equal to b, then is it possible that if x tilde maximizes f x? So, is it possible that if x tilde maximizes f x? Let us try to answer this. We will not go into the detailed derivation. We have shown that for a symmetric matrix A, it is given that A is square and symmetric. It is very very important. So, what is A? A is square and symmetric matrix. We have derived in one of our lectures that if A is square and symmetric, then gradient of f equal to 0 will lead to Ax equal to b. Now when we say that gradient of f equal to 0 will lead to Ax equal to b, we imply that it is an extremization problem. Setting gradient of f equal to 0 does not automatically tell whether it is a minimization or a maximization. Later on we have shown that if A is also positive definite, then it leads to a minimization problem and not a maximization problem. But if that constraint is not given, then it could be a maximization or a minimization problem. Setting gradient equal to 0 does not necessarily imply that it is a minimization problem. It could be a maximization or a minimization problem. In the next step, when we set that it to be a positive definite A to be a positive definite matrix, then we can show that it is indeed a minimization problem and not a maximization problem. Okay. The next question. The next question is, what is the basic reason behind a numerical scheme to exhibit false diffusion in a convection diffusion problem? That is the first part. Then, can central differencing turn out to be superior over upwinding in order to minimize such effects? You have to justify your answer. So, again we have discussed about this issue in details in one of our lectures, but just to summarize, that if you have a flow which is misoriented with respect to the grid lines, that is not parallel to the grid lines and inclined significantly with respect to the grid lines, then that misorientation can give rise to an artificial diffusion that is even if there is negligible or very low diffusion or zero diffusion, it artificially represents a diffusion between or mixing between two fluid streams, and that essentially shows that the false diffusion or numerical diffusion is mostly attributed to the orientation of the flow direction with respect to the grid lines, and that is the main cause behind false diffusion. Now whether the central differencing scheme can address it is a debatable issue, and there are cases when it cannot address it because the central difference scheme will not work for very high Peclet number flows, and for very high Peclet number flows where the diffusion is insignificant in practice, any numerical artifact in diffusion can bear significant consequences, because you are not having significant diffusion in physical reality, but numerically significant diffusion can creep up, and for high Peclet number flows what we can see is that the central differencing scheme itself is vulnerable. So that is the answer to this question. Next question. For a one dimensional convection diffusion problem, it is given that the fluid density is 1000 kg per meter cube, flow velocity scale is of the order of 1 meter per second, diffusion coefficient is 10 to the power minus 9 meter square per second, and domain length is 1 meter. Question is, will a central difference scheme work for numerical solution to this problem given that the dimension of the solution vector for TDMA should not exceed 1000. That means you should not use number of grid points of the order of more than 1000. Give reasons to your answer. So here as a very simple approach, what we will try to do, we will try to calculate what is the cell Peclet number and see whether the cell Peclet number is less than 2 or not. So the characteristic delta x is of the order of L by 1000. So that is 10 to the power minus 3 meter, that is the characteristic grid spacing. It is just an order. Of course if you have non-uniform grids, it is true that the grid spacing may differ significantly from this one, but this is just the order of magnitude of the grid spacing. Now what is the Peclet number? Cell based Peclet number, advection strength by diffusion strength. So what is gamma? Gamma is rho into d, rho into the diffusion coefficient is rho into the, because the units if you want to match this, d is a kinematic unit. So you have to convert it, just like if you consider it as a fluid flow problem, this becomes viscosity. So you have to convert the kinematic unit into the dynamic unit. So that is why you have to multiply it by rho. So the two rho's get cancelled out, so it is of the order of u delta x by d. So u is 1, delta x is 10 to the power minus 3 and d is 10 to the power minus 9. So it is of the order of 10 to the power 6. So it is a very high cell based Peclet number, which implicates that the central difference scheme will not work, it is much greater than 2. So the only key towards answering this question is one has to be careful, it is not the global Peclet number but the cell Peclet number. So it could happen that the L based Peclet number is greater than 2 but delta x based Peclet number is less than 2. Then if such numerical data is there, then central difference scheme would still work. So if you want to make central difference scheme work here, you have to use such a defined delta x such that u delta x by d has to be less than 2. So it has nothing to do with the total length of the domain, but it has something to do with the cell spacing. Next question. There is a statement given simple algorithm is not fully implicit and therefore it is conditionally stable. Is this statement correct? Justify your answer. I am repeating it again. The simple algorithm is not fully implicit and therefore it is conditionally stable. Is this statement correct? Give reasons. So again we have discussed about this extensively in one of our lectures. So the semi implicitness of the simple algorithm has nothing to do with time discretization. So it has something to do with the omission of sigma ANB UNB prime, the neighboring velocity correction terms in the formula for velocity correction and also in the formula for pressure correction. So that particular effect leads to the consideration of the semi implicitness of the simple algorithm. It has nothing to do with the time discretization effects like implicit, explicit, Crank-Nicolson scheme. So one did not confuse those with this effect, therefore there is no issue of conditional stability here, it is unconditionally stable. Next question, what is the basic geometrical difference between a structured and an unstructured mesh? Can you have rectangular subdomains in an unstructured mesh? Give reasons. So again we have discussed about this, but just to summarize, if you have a structured mesh then you have the same connectivity of one vertex with the neighboring vertices, whereas if you have an unstructured mesh you may have different connectivities between the vertices. So one vertex may connect different number of neighboring vertices depending on which vertex you are considering, and because such a structured layout is there for a structured grid, you can express the grid locations or the coordinates by using indices I, j, k like this depending on the dimensionality, whereas you have to explicitly specify the coordinates without referring to such grid line orientations I, j and k to specify the coordinates, specify the locations of the vertices, and then you have to establish suitable connectivities. If you consider about the issue of having a possibility of a rectangular unstructured mesh. So if you can see for example that here you have a vertex in this. So this vertex connects to how many neighboring vertices? 1, 2 and 3. On the other hand, if you consider this vertex, it connects how many neighboring vertices? 1, 2, 3, 4. So it is possible that you can have an unstructured mesh with rectangular grids. You can of course have also combinations, like you can have combinations of triangular, rectangular and all sorts of combinations are there. So it is very much possible that you can have unstructured mesh with some control volumes that are rectangular. Next question, for a flow under 0 pressure gradient, necessity of a staggered grid will never arise. Is this statement correct? Give reasons. So I am repeating the question again, for a flow under 0 pressure gradient, necessity of a staggered grid will never arise. Is this statement correct? Give reasons. See, the necessity of staggered grid was mainly there because of what? Because of interpolation of pressure at the faces of the main control volume, where pressure data is not directly available. So you have to interpolate. So if there are situations when the pressure gradient is 0, then the requirement of pressure interpolation is nullified, pressure no more acts as a variable. But there is a catch word, if you are going through the root of the continuity equation, then you can have a checkerboard type of velocity field if you express the continuity equation in the normal grid sense that we have discussed. So it is issue of whether you need to go through the root of the continuity equation or not. If you need to go through the root of the continuity equation, then irrespective of how do you handle checkerboard type of pressure fields, whether pressure that is necessary or not, you also have to handle checkerboard type of velocity fields if you have to go through the roots of the continuity equation without staggered grids. Of course, that again can be rectified with some special interpolation schemes, but if you do not use a special interpolation scheme or just consider a linearized interpolation, then the continuity equation itself can give rise to wavy or checkerboard type of velocity fields even if the velocity is a constant. So that means if you consider we have shown that du dx in a one dimensional problem, if you have du dx equal to 0, it will be reflected in terms of u capital E is equal to u capital W, the effect of P will be gone. So that means if you have a velocity here as 10 and velocity here as 10 and velocity here as 0, 10, 100 whatever, all will be interpreted as same. So by this is what we mean by the checkerboard type of field or a wavy type of field. So irrespective of the value here, the continuity equation here may be satisfied ambiguously with many possible values of up. So that is one of the artifacts. So the question remains whether we have to go through the root of the continuity equation. Many times we do not have to go through the root of the continuity equation. If you have a unidirectional flow, you already know what is the velocity distribution and it is just a constant value that you know already. So if you do not have to go through the root of the continuity equation, just have to solve the momentum equation with dp dx equal to 0, then you do not have to bother about staggered grid, because then it is an issue of pressure interpolation only and that need not be taken care of when the pressure gradient is 0. So that is what we have to keep in mind. Next question, what is closure problem in turbulence modeling? So this also we have discussed, but let us again summarize that in turbulence modeling we come up with the Reynolds average Navier-Stokes equations, where we basically decompose all the quantities in say the velocity in terms of the mean and its fluctuation, substitute that in the Navier-Stokes equation and take the average. Once you do that, then new stress terms appear del del xj of rho ui prime uj prime bar uj prime. So this particular expression gives rise to new unknowns. What are these new unknowns? New unknowns are rho ui prime uj prime average. So when you consider this rho ui prime uj prime average, these are new unknowns. So because it is symmetric, you have I ranges from 1 to 3, j ranges from 1 to 3, there could be 3 into 3 9 unknowns, but because I and j are interchangeable and symmetric, you have 6 independent unknowns. So these new unknowns do not have matching number of governing equations and they need to be closed by suitable modeling. So you do not have matching number of equations with unknowns when you come up with the Reynolds average Navier-Stokes equation, and you need to close this extra number of unknowns by appropriate modeling effort, and that is known as a closure problem in turbulence modeling. Okay. Now next let us go to some questions which are bit longer answer type. The next question, consider the following template one dimensional wave equation: del u del t plus c del u del x equal to 0. You are using a modified FTCA scheme where in the time discretization you express the term ui superscript n as half of ui plus 1 n and ui minus 1 n summation, where the index I represents spatial discretization and the superscript n represents temporal discretization. So, this is the problem. You have to examine the stability of this scheme by von Neumann stability analysis, that is the question of the problem. So, let us try to express this del u del t as, so it is a forward differencing in time. So, ui n plus 1 minus ui n divided by delta t plus c del u del x is the central space. So, u I plus 1 n minus u I minus 1 n by 2 delta x, so first order central differencing equal to 0. Now, next is that you are given that ui n is equal to this one, which needs to be substituted here. So, once that is substituted, let us write what we get. So, we get ui n plus 1 minus half ui plus 1 n plus ui minus 1 n plus c delta t by 2 delta x into ui plus 1 n minus ui minus 1 n. So, now c delta t by delta x we define as the Courant number. So, you can write ui n plus 1 is equal to half minus Courant number by 2 into ui plus 1 n plus half plus Courant number by 2 ui minus 1 n. So, you can write the corresponding perturbations. Epsilon I n plus 1 is equal to half minus Courant number by 2 into epsilon I plus 1 n plus half plus Courant number by 2 epsilon I minus 1 n. Next, what we will do? We will substitute epsilon x t is equal to e to the power alpha t into e to the power j k x, where j is square root of minus 1. So, you have e to the power alpha t plus delta t, we are doing it for the left hand side, into e to the power j k x is equal to half minus Courant number by 2 e to the power alpha t e to the power j k x plus delta x plus half plus Courant number by 2 e to the power alpha t into e to the power j k x minus delta x. So, we divide the left hand side by e to the power alpha t, so that the amplification factor becomes e to the power alpha t plus delta t by e to the power alpha t. So, that will be equal to the right hand side we divide by e to the power j k x. So, it becomes half minus Courant number by 2 e to the power j k delta x plus half plus Courant number by 2 e to the power minus j k delta x. So, you can define k delta x equal to theta. So, this is half minus Courant number by 2 e to the power j theta plus half plus Courant number by 2 e to the power minus j theta. So, half minus Courant number by 2 cos theta plus I sin theta plus half plus Courant number by 2 cos theta plus j sin theta cos theta minus j sin theta. So, you can write this as half cos theta plus half cos theta. So, cos theta minus Courant by 2 cos theta plus Courant by 2 cos theta. So, that cos theta goes, then half j sin theta minus half j sin theta cancels, minus Courant number by 2 j sin theta minus Courant number by 2 j sin theta. So, minus Courant number j sin theta. So, amplitude of A is square root of cos square theta plus Courant square sin square theta. This must be less than 1 for a stable scheme, and 1 you can write as root over cos square theta plus sin square theta. So, from here you can write that Courant number square minus 1 sin square theta must be less than 1. So, that means Courant number must be less than 1 to make this strictly valid for all possible values of sin theta. So, you have to remember that Courant number cannot be negative. So, we are only dealing with the less than 1 sign, we are not considering the mod case here, because it is, we are considering it to be any number 0 onwards, because C delta t by delta x, C is positive, delta t is positive and delta x is positive. Okay. So, the summary is that it is a scheme which is conditionally stable, it depends on the value of the Courant number, that must be less than 1. Okay. We go to the next question. The next question is, consider a one dimensional steady state convection diffusion problem without any source term. Derive a profile assumption for variation of the dependent variable. I am repeating, derive a profile assumption for variation of the dependent variable in the advection term following the quick scheme. And considering the same profile assumption for the diffusion term, derive the complete discretization equation for the convection diffusion problem. That is the first part. So, this we have done in the class in our previous, in one of our previous lectures. Just to summarize, the quick scheme refers to quadratic upstream interpolation scheme for convective kinetics. So, if you have grid points like I minus 1 and I plus 1, and if here is the interface, then you use the interface interpolation, you use a profile for interface interpolation where you use 2 upstream points and 1 downstream point. So, you can write phi as a0 plus a1x plus a2x square. For your convenience, you can select x equal to 0 here, and then you can write a0, a1, a2 in terms of phi I minus 1, phi I and phi I plus 1, by noting that when x equal to 0, phi equal to phi I, when let us say this is delta by 2 and this is delta. So, when x equal to delta, phi equal to phi I plus 1, and when x equal to minus delta, phi equal to phi I minus 1. So, if you use these conditions, you will get a0, a1, a2 in terms of phi I minus 1, phi I plus 1, And then for the advection term, so what is the difference between the advection and the diffusion term? For the advection term you require rho u phi at the interface. So the interface is located at x equal to delta by 2. So once you know a0, a1, a2, then you substitute x equal to delta by 2 to get phi at the interface. This is phi at x equal to delta by 2. This is a generic way of finding phi at the interface. What is for the diffusion term? You require d phi dx at the interface. So what is d phi dx? D phi dx is a1 plus 2 a2x at x equal to delta by 2. So this is the only slight difference, but important difference between the derivation that we made in the class and this derivation. In the class, for the diffusion term, from the beginning we assume that it is a piecewise linear profile. Now we are not assuming that it is a piecewise linear profile for the diffusion term, we are using the same profile for interpolating the advection term and the diffusion term. So then you can assemble the advection and the diffusion terms in the advection diffusion discretization equation, that is d dx of rho u phi is equal to d dx of gamma d phi dx. So you can have integrate this one from small w to small e. Remember, small w and small e are interfaces. So rho u phi at small e minus rho u phi at small w is equal to gamma d phi dx at small e minus gamma d phi dx at small w. So if you consider a grid layout, you have P, capital E, capital W, small e, small w, and you have to keep in mind that if this is the interface, then this is I minus 1 and this is I plus 1. On the other hand, if this is the interface, then you require another grid point WW, where you say that this is I plus 1 and this is I minus 1. So it depends on what is the interface. So with the blue color I have represented the situation where W is the small w is the interface, and with the black color I have represented a situation where small e is the interface. So these two interfacial conditions you require for evaluating these terms, and then you can assemble. If some of the coefficients may be negative or some of the coefficients may be of opposite sign than the other coefficients, then you have to conclude that the scheme is conditionally stable, and you can find out the corresponding stability criteria. So from the basic rules you can evaluate that it is simple algebra remaining after this exercise, and you can extend this. So the next part of the question is extend the derivations to one dimensional unsteady state convection diffusion problem with fully explicit time discretization. So if you add an unsteady term to the problem, then it requires the two important considerations. What are those two important considerations? One is the integration of this with respect to time and then with of course with respect to x. So it will become from time t to t plus delta t, small w to small e. So rho p phi p minus rho p naught phi p naught by delta t into delta x. By delta t will come if you divide both the right hand side and left hand side by delta t. Let us not do that at this stage and do it straightforward. So rho p phi p minus rho p naught phi p naught times delta x. So this is the transient term. What will be the consequence of fully explicit scheme in the other terms? The consequence will be that everywhere in all other terms phi will be the phi at the beginning of the time step, phi with superscript 0. This is very critical. So that is the difference between the explicit and the implicit scheme. If it was an implicit scheme, then in the right hand side, in the other terms, phi would be phi at the end of the time step, phi at t plus delta t. Now because it is fully explicit scheme that is asked in the question, it should be phi at t, not phi at t plus delta t. So all other phi's expressed in terms of the discretization that we have already derived, there you have to substitute phi as phi naught, that is the only difference. Okay, let us go to the next question. We consider a one dimensional constant density flow, a one dimensional constant density flow where the momentum equation, so the constant density flow situation is shown in the figure where you have uniformly spaced grid points. The velocity grid points and the main grid points are shown separately, it is a staggered grid arrangement. The momentum equations for ub and uc are given. So ub is equal to 5 plus 2.5 into p1 minus p2 and uc is 5 plus 7.5 into p2 minus p3. The boundary conditions are given, ua equal to 15, uc equal to 15. All values are given in consistent units. Obtain the values of, question is what are p1 and p2 using simple algorithm based calculation procedure. Comment on the uniqueness of your solution. So if you want to follow a simple algorithm based procedure, what is the step 1? You have to guess a pressure field. So let us say P1 star equal to 0, P2 star equal to 0, P3 star equal to 0. We know that these are not correct, but just guess is a guess, we can always make incorrect guesses. So based on that, see what momentum equation we will solve. We will solve ub momentum equation to get ub star. We will not solve uc because uc is already given, why should we solve it? So ub star is equal to 5 plus 2.5 into p1 star minus p2 star, so that is equal to 5. Next is you have to solve the pressure correction equation. So you have to derive the pressure correction equation. So what you have to do, you have to consider the continuity equation. So for the continuity equation, for considering the grid point 1, the control volume surrounding 1, du dx equal to 0 is the one dimensional continuity equation that will give you ub equal to ua. What is ub? ub equal to ub star plus db into p1 dash minus p2 dash, and that is equal to ua. Because ua is given, there is no question of writing it in terms of a correction formula. So let us substitute the values, ub star equal to 5, then dB is 2.5, that is given here in the momentum equation itself. The correction equation will look like the momentum equation with differences as the correction terms. So what will be P1 dash minus P2 dash, that is equal to 4. Then if you can write the momentum equation for the grid point 2 also, control volume surrounding 2. So what will that give? That will give uc equal to ub. uc is given as 15. So you have 15 equal to again 5 plus 2.5 into P1 dash minus P2 dash. So it will give rise to same equation, P1 dash minus P2 dash equal to 4. So you can see that by considering the two different grid points you are basically getting only one independent equation, not two independent equations. It shows that this pressure correction is a relative quantity. So what will be the values of P1 dash and P2 dash depending on what you choose as an initial guess for one. So for example, if you choose P1 dash equal to 0, then what will be P2 dash? That will be equal to minus 4. So what will be then P1? So then you can also calculate what is new ub based on this correction. So step 3 ub is equal to ub star plus db into pp into p1 dash minus p2 dash. So ub star is 5, db is 2.5 and p1 dash minus p2 dash is 4. So this makes it 15. Without testing anything you can readily check for this problem that ua equal to 15, ub equal to uc equal to 15 and now ub equal to 15. So for one dimensional flow u is a constant, so in one step it has just converged. And what will be the value of P1 and P2? So step 4 P1 is equal to P1 star plus P1 dash, so that is 0, and P2 is equal to P2 star plus P2 dash, that is equal to minus 4. So you can see here is that depending on the choice of P1 dash you could get different values of P1 and P2 combinations, but the difference will always be 4. So it is the pressure difference that remains preserved, but absolute values of pressures depend on the choice of the initial guess. So it is not a unique solution of pressure, it depends on what is the guess that you take for one of the pressure corrections. Okay. Now we have two more questions which we will go through a bit quickly because these questions we have already discussed in full details in some of our lectures. So the next question, you have a steady hydrodynamically fully developed flow in a parallel plate channel. So first it is a steady flow, so del T term is 0. Hydrodynamically fully developed flow in a parallel plate channel means you have only u but v equal to 0. It is a two dimensional flow with a uniform velocity over the cross section. So u equal to u average which is uniform over the cross section, so it is a plug flow. Thermal conductivity of the fluid is so small that the heat diffusion effects can be neglected. That means the thermal conductivity, the conduction term in the advection diffusion equation you can neglect. Further you have a volumetric sink term which can be expressed as H into Tm minus T infinity by L, which is a heat loss term. And what is this Tm? This Tm is the bulk mean temperature of flow, and it is also given that H by rho Cp U average is equal to 2, where H is the heat transfer coefficient and L is the channel length and T infinity is the ambient temperature. And for solving this problem you can assume that del T del x is equal to dTm dx. Here rho is density and Cp is specific heat. So what is the problem? The problem is that if the inlet temperature, that is at x equal to 0, if T is Ti, then obtain the variation of theta is equal to Tm minus Ti by T infinity minus Ti as function of x by L. So we will just quickly derive the governing equation. The unsteady term is not there, so ddx of rho u Cpt is equal to, there is no diffusion term, the diffusion because thermal conductivity is 0 and there is a source term minus H into Tm minus T infinity by L. Given that U is U average, so you have, and all the other properties we assume as constant. So ddx of, so we have dt dx, so we cannot write really dt dx because t could be a function of both x and y, although u is a function of x only, but t could be a function of both x and y, so better write as del x instead of ddx. So we can write del t del x is equal to minus h by Tm minus T infinity by L rho U average Cp. Now instead of del t del x you can write as dTm dx, that is given in the problem. Now if you define theta is equal to Tm minus Ti by T infinity minus Ti, then what you will get? So d dx of Tm minus Ti by T infinity minus Ti. So here you can write Tm minus Ti minus T infinity minus Ti by T infinity minus Ti in the right hand side minus H by L rho U average Cp. And you can absorb this L by expressing a non-dimensional x, that is small x by L. So if we consider say y is equal to small x by L, then this is defined as theta. So d theta dy is equal to H by rho Cp U average into 1 minus theta, and this is given as 2. Now recall, this is exactly the same governing equation with which we dealt in one of our worked out examples during solving the convection diffusion problem. D theta dy is equal to 2 into 1 minus theta. So based on this you can find out, you can integrate this by using the upwinding scheme which is given in the question. So the question is, determine the non-dimensional temperature theta as a function of y using the upwinding scheme. Take 5 uniformly spaced grid points for your computation and solve the resultant system of algebraic equations by TDMA. So we have solved this problem exactly in one of our lectures. So I just formulated the problem because the formulation of this problem is different from the problem that we derived or we discussed with in one of our lectures, but once this problem is formulated, the final form of the equation is same as the equation that we dealt with in one of our lectures. So you can use the same derivations for solving this problem using an upwind scheme. So here you have an upwind scheme where you have an advection term, source term, but zero diffusion term. That is what you have to keep in mind. Then the final question, let us go through. The variation of nutrient concentration, sigma outside and within a malignant tumor colony, that is a domain of cancerous cells, is governed by an approximate equation characterizing diffusive equilibrium. So let me repeat, the variation of nutrient concentration sigma outside and within a malignant tumor colony, that is a domain of cancerous cells, is governed by an approximate equation characterizing diffusive equilibrium as del square sigma equal to 0. Taking an unstructured triangular mesh simulating an approximate 2-dimensional version of this problem, derive appropriate discretization equation for solving the distribution of sigma. So I repeat, taking an unstructured triangular mesh simulating an approximate 2-dimensional version of this problem, derive appropriate discretization equations for solving the distribution of sigma. So we need not go through any more details of this derivation because this is of the form del dot gamma del sigma equal to 0 where gamma is equal to 1. So it is a pure diffusion problem, and if you consider an unstructured mesh like this, with the control volume layouts around a triangular shaped control volume, the neighboring control volumes shown here. So you can, we have seen that how to discretize a general problem del dot gamma del phi equal to 0. In the class we derived where we had phi equal to u for the velocity. So and gamma was the viscosity. So here gamma is 1, and instead of velocity we are now dealing with the sigma as a variable, but in mathematical terms the problem does not differ anymore from what we derived in our class. So you can use the same derivations to decompose it in the form AP sigma p, or instead of p we will call it C0. So AC0 sigma C0 is equal to AC1 sigma C1 plus AC2 sigma C2 plus AC3 sigma C3 plus B, where in B you have terms involving sigma 1, sigma 2, sigma 3, and the corresponding fluxes are known as non-orthogonal diffusion fluxes. So these fluxes are functions of the difference between the values of sigma of the vertices of the triangle, whereas these are the values of sigma at the centroids of the main control volume. So you can write it in a similar way as that of the standard convection diffusion equation, standard diffusion equation for a structured mesh, where you have the values expressed in terms of the differences of the values at the centroids of the neighboring control volumes, but because of the unstructured nature of the mesh you also have some non-orthogonal diffusion flux which will appear in this. So this includes non-orthogonal diffusion flux. So considering this, it is a straightforward derivation, and this derivation can be done by following our lecture notes on unstructured mesh. So we stop here today. Thank you very much.